Before we get into TCP flags, which are really the last big thing we're going to talk about here, I want to talk a little bit about TCP options. Now, earlier I specified the RFC that defined TCP, and there were some follow-ons, of course, to that enhance it. But one of the big features of TCP is the ability to support options, which are typically defined through other RFCs, which provide new features. And some of those new features are kind of edge cases for very specific use cases, but some of them are actually enhancements to TCP that followed later on. So this was kind of a forward-looking concept, and you can have a whole lot of different options included with the TCP packet. Now, we talked about options with IP packets and how they're rarely ever used. Most of our IP headers are generally only 20 bytes without any options. TCP is a little bit different in that options are actually used quite frequently. As a matter of fact, most of the time you're looking at TCP packets in the real world, you'll probably see options, a list of various options being used. So I'm not going to go through those in too much depth. We've kind of de facto gone through some of them. We talked about some of the window scaling stuff earlier and selective acknowledgement a little bit, but I do want to highlight some of the more common ones you'll see. One of those is maximum segment size, or MSS, which is the largest amount of TCP data a host can send across the network. We have the timestamp, which is not something we've looked at, but we will look at it later when we talk about latency and troubleshooting that, because it's used to calculate round trip time, which is important for some of the latency recovery issues or features, I should say, that TCP has. We've already talked about window scale, which allows window sizes to scale larger than the 2-byte maximum that the window size field provides by essentially becoming a multiplier. So that's something you'll see quite often. And of course, selective acknowledgement, which allows acknowledgements of non-contiguous segments. That feature is really an efficiency such that if a system detects that a TCP segment was not received, rather than having to retransmit an entire stream of data, it can now retransmit just the missed portion in the non-contiguous segment. So that's a pretty important feature as well, and something you'll see enabled in most places. The packet you see on the screen here has some TCP options in it. I just want to show you what those look like. In this case, we have our TCP header expanded. If I scroll down to the bottom, you'll see that we have options listed here. If I click on that, you'll see that's the last portion of the TCP header. It's always at the end of it. If this was a TCP data packet and there were data, you would see additional data after this. But since this is a TCP control packet, in this case, an initial SYN, you only see the options at the end. And in this case, we have 12 bytes of options. Wireshark summarizes them for us on this line. We see several of the things we talked about. For instance, we see the maximum segment size, which is 1460 bytes. We see our window scale, which is used to define the maximum window size for this host. And we see that selective acknowledgement, or SAC in this case, is permitted, and it has actually a couple of options associated with it. One to tell us that the SAC is permitted, and one to tell us that the length value is 2. So some of these fields will be very simple. They'll just be a binary yes or no. Some of them will have additional options or values with them, like maximum segment size, which in this case has a specific length and value associated with that. So you'll see a few different TCP headers as you go along that contain different types of options. So best bet, if you want to learn about those as you see something you don't understand, just Google around for it. You'll be able to find the RFC, which is probably going to be a little dry, but it'll be the gospel source of truth. But otherwise, you'll probably find some good resources. Most of these are pretty well documented, and eventually you'll get to the point where you recognize most of the ones that you see. Switched over to the command line here quickly because I want to show you how T-Shark shows some of this information as well, and it's line-based data. In this case, I'm just looking at T-Shark-R http google.pcap, and I'm only showing the first 5 packets. Now, when I do that, we get the line-based data, but notice at least on the TCP control packets here, where we're actually seeing the TCP data because it's the highest layer of information available, we actually see some of these option values listed. So for instance, we see MSS equals 1460, we see window scale equals 4, that's WS equals 4, and it's kind of bleeding over across the line boundary in this case, but we see SAC perm equals 1, which is telling us selective acknowledgements are permitted. So in cases where the info column is actually showing you the TCP data, in T-Shark you'll actually see that information, the specific TCP option information listed here as well out beside that. So that's a nice handy feature of looking at TCP paste data in T-Shark. The last big feature of the TCP protocol header that we're going to talk about is probably the most important, and I've saved it for last because it really defines how stimulus and response is working for TCP packets, and that's the flags section you see there, beginning at TCP 13. So of all the packet byte locations that people who look at a lot of packets remember, TCP 13 is at the top because it's there you find all the different flag combinations, and you often end up writing a lot of filters to filter based upon those specific flag combinations. But the most important thing to consider and remember here is that this section and the presence or absence of certain flags being set is what ultimately defines the purpose of the TCP packet. Now, when I say flag versus value because a flag is essentially just a single bit field. So this 1 byte field is made up of 8 bit fields, and each one has a different value. Simply by being set to 1 or 0, that value is either enabled or disabled. So you see on the screen here, we see those 8 different values, and they're mapped to the specific positions within the byte, of course, starting 1, 2, 4, 8, so on, binary numbering there. So we see those fields listed there, and I want to talk about one concept which I've alluded to and hit on a little bit already, and that's the concept of a control packet versus a data packet. So anytime you see a packet that has a TCP header with no data following it, that's a TCP control packet, and it's used to pass information between hosts related to the TCP protocol itself. So for instance, that's where we see our initial connection setup, our handshake, where we see that initial send, SYNAC, and ACK. Those are control packets. When I send data to a device and receive an acknowledgement back, that acknowledgement doesn't have any new data payload with it, no application layer data. So it is a control packet. Same with terminating a connection. So with FIN packets, FINACs, with abruptly halting a conversation, with a reset, those are control packets, and we'll see a lot of those. Data packets are those packets that are actually followed by data. So if you're looking at the contents of the packet, you will see generally either just some raw data following the TCP header, or better yet, an application layer protocol and its header following the end of the TCP packet. So we've gone through a lot of examples, and hopefully you kind of see what I'm talking about there just based upon what we've already gone through. We'll continue to highlight the difference between control packets and data packets. The key takeaway here is the flags are ultimately more commonly associated with one versus the other. For instance, a packet with the send flag set to on is generally always going to be a control packet. Now, that's not to say you can't mess with that and you can't shove some data in some places it isn't supposed to be, even some places that are maybe okay per RFC spec but not really handled properly by certain operating systems. But for the most part, when you see a send flag, that's generally going to be a control packet. Same with a reset and a fin and so on. So basically, the different flags being set means different things regarding whether something is a control or a data packet. Now, I want to go through the different flags here. We're not going to go through all of them because honestly, all of them aren't generally used in normal communication. We're going to focus on skipping the first two here. So we're going to skip CWNR, R, and ECE. We're going to focus on the other ones. Urge, ACK, push, reset, send, and fin. The last 6 or the rightmost 6 in this case. Now, I'm going to talk through each one of these flags individually, just real briefly, give you a real brief description, and then we'll actually learn about the purpose of the flags as we talk about TCP, normal and abnormal stimulus and response. I think with this example, it's always better to learn about the TCP flags through practice rather than just me talking about them. So I'll actually look at packets and examples of stimulus and response to do that. First of all, we have the SYN flag, and when the SYN flag is set, that's generally used to establish a new connection. So you'll notice in all the packet captures we've already looked at that are TCP based, you always see a TCP SYN packet, a control packet, which establishes that new connection. We also have the concept of an acknowledgement packet, or one with the acknowledgement flag sent. And this generally acknowledges the receipt of a packet with the correct acknowledgement number. So remember the interplay between sequence and acknowledgement numbers. We have that sequence number coming in plus the amount of data transferred, and that's our acknowledgement number. So our ACK packets are what's used to transfer those numbers back to the host in response that sent the initial packet, whether that's a SYN or a data packet. The packet type that complements a SYN is a fin, and a fin is a finish, and that is what gracefully terminates a connection. So this is going to be a TCP control packet when this is set, and it's used to terminate a connection when no more data is being sent. Now, I say fin is graceful. Reset is kind of the opposite of that. It's more abrupt, and it abruptly terminates a connection. So you'll see resets a lot if you try to connect to a host that doesn't want you to connect to it. So maybe the port is closed or something's blocked, so it'll send a reset to abruptly halt that connection. Or in some cases, you'll see a reset when a connection is very abruptly halted midstream. Maybe something has gone wrong on the host you're communicating with or something like that. So a fin is more like, gracefully saying, okay, I'll talk to you later, bye-bye, and a reset is more like just hanging up the phone. So that's the best way to think about those and when those specific flags are set. Finally, we have the concept of push, which is really used to facilitate real-time communication by forcing data to be processed immediately. And so the definition of push is kind of tricky, but the important thing to note here is that push is set when instructing a host to automatically or very quickly, immediately send its data buffer over to a system. So you'll see push flag set when data is being transmitted, talking about data packets versus control packets. So that's the simple description of each of these flags and what it means when they're set. Now, it's important to note that it's not a case where only one flag will ever be set. In many cases, you'll see flags paired together. For instance, you see ACK paired with a lot of things for efficiency's sake. You see SYNs and ACKs paired together, fins and ACKs, pushes and ACKs, and so on. So there are combinations of these flags that are acceptable and that mean certain things, and there's combinations that are a little odd and unexpected and may be used either by bad guys to try to do something funny or try to crash a TCP stack somewhere, things like that. So again, instead of going through just these in this way and just describing them, I'm actually going to get in next to specific stimulus and response, and we'll talk about what it means when combinations of these flags are set and how systems will interpret these and all of the weirdness that kind of comes along with that. So stimulus and response, and actually looking at some more theory and actually digging into some packets related to TCP flags is what's next for us.